back online, let us focus on the types of radioactivity. Types of radioactivity. Remember, I mean radioactivity. So generally, as I said, disintegration of atomic into stable ones. So we have radioactivity can either be natural or artificial. So natural radioactivity, this happens without human interference. So atom may disintegrate without human interference. For example, lead that have atomic number 2, thorium 238 to 234 radium to 226 etc. so on. Artificial or induced radiation. So this is done by exposing stable natural occurring nuclei to different conditions. Next part gives an example how induced radioactivity can be achieved. For example, neutron bombardment. You can also do that by bombarding with an atom of neutron. For example, uranium 92. So sisi andiwani pamwamba. So uranium sasinta. Ukakauti point 2 kakutiro kita bombandi alpha, then you know already kuti alpha imanena kuti sinta atomic number sinta by 2. Atomic number by 4. Generally, so there is a combination alpha here. So here and here 11. So that's why here take 11 since neutral 0. Here 19 plus 4, that's 23. So we have 22 plus 1, 26. So 23 also 23. 9 also 9. That's what we can say about. Another thing is about source of radiation. As you said, there is natural and artificial. So source of radiation can be categorized into natural and the artificial. Maybe categorized into natural and the artificial. So under natural source of radiation, we have cosmic radiation. So these are radiation from the sun. We have terrestrial radiation. These are radiation from the ground now. And we have internal sources. Under internal sources, these include our body. So under natural source, we have cosmic radiation, terrestrial radiation, and also internal sources. In artificial sources or human sources, we have medical radiation. We have a good example. We have X-rays. We have some similar properties of gamma rays, as we discussed already in the previous video. Consumer products like a TV, they may also have their own radiation. Consumer product TVs, other luminous dial watches, some smoke detectors, etc. Atmospheric testing of nuclear weapons so those equipment may have different they are some of the source of radiation. So how can we detect radiation? So there are the instruments that are used to detect the radiation. So for example, we have photographic plates. My instrument are some of them long, so just know them. So we have photographic plates, we have scintillation counter, we have spark counter, we have GMT, that's giga neural tube, and so a gold leaf electroscope. Those are some of the instruments that are used to detect radiation. As I said, photographic plates, filtration counter, a spark counter, giga neural tube, gold leaf electroscope, and also other radiation detectors include Bab chamber, Wilson couch counter, solid state detector, and the match counter. Decay curve and half-life. So we have to look at the half-life and the decay curve. Okay, half-life is the number of particles that can decay by half of its. For example, ngatina 20, for example, an atom in 20, 20, suppose 20 neutron. Okay, 20 mass in other way. So how long does it take for it to decay? So if you imagine that by half, the car easier decay from 100, from 20 to 100, from 100. That's radiation, depending on the that's half-life chain. The number of valent nuclei decreases exponentially with time, and as a result, it is known as exponential law of radioactivity. So the radioactive decay is measured with activity per second, or degradation per second. SI unit is called Becquerel. So here's the formula. This formula is here. This formula is here. This formula is here to help us to calculate the number of radiation. So that is generally this formula may be expressed into this formula, where T is time taken for decay, and the capital T is time taken for decay, and the small capital T is half-life. So NO is number of original amount. This NO, number of original amount, half T over small t. So T is time taken and small t is half-life. NO is original, this is half already, that the half that you know. N is amount remaining. Okay. Generally, whenever we want to use this one, any amount that is remaining, any is original one. So original amount, any the one remaining, original amount, then this formula, half over t time remaining and time taken. T is time taken and the small t is half-life. Let us see how best we can apply to solve that problem. Half-life is time taken for half of nucleus to remain, or time taken for half of atoms in a sample to decay. Half of time of an atom to decay, or time taken for half-life nucleus to remain. So that's how you can define a half-life. Let us see the example. Here is the example. Example is half-life. There will be 30 grams. After the further half, there will be 15, then 70.5. So that's what I've explained already. So as I said, you can use this formula to calculate anything that you want related to the formula. Let us have an example. Given that radioactive particle of bismuth has 210, that's grams mass. Half-life in 5 days. Note after 5 days, as the disintegrate the 5 days. If originally there are 80 grams of bismuth, 210 determines the amount that would be remain after. So after 5 days and after 15 days. So how? Well, straight there would be 0 in an 80, there would be original mass 80, there would be 0 minute. After 5 days it has 40, time again amount remaining. After 10 days it has 20, after 15 days it has 10, so on and so forth. You see? Now for us to come up with the formula, we say by using formula N is to 0, N in the amount that is remaining, NO in the amount remaining. Half-life in the 5 days. Also, time taken 5 days as well. So think with the formula, any the amount that is many. So but just substitute formula with n on 80, half into 5 over 5, 5 over 1. So if you do simple math calculation, it will be 40. Now after 5 days, question 1. What about if you eat after 15 days? So we have to apply the formula part B, any the amount that you don't know, NO original one. So original one 80, half T 15 after 50, 50 over 5, 3. So half to the power 3, the 1 over 8. 1 over 8 times 80, that's 10. 10 grams. The amount that makes 10 grams. So generally, whenever you ask, just memorize this formula, and you know the teacher says what does that stands. Any the amount that is named, any on the original one, half the numbers, you know. T is time taken for it to decay. But many T one the half, like so. That's the simple formula for you to use whenever you have a problem of such kind. So table below shows some elements and their half-lives. So that table there just indicate some elements. For example, thorium 10 to the power, so a lot of years, and so on and so forth. Simple calculations all over, and also a graph. All right. So that's all about it. Thank you.